Welcome to another lecture on linear algebra. Today we are going to talk about spanning sets and linear independence. Let's go take a look at list of topics for today. So we have a rather long list of topics to talk about, and let's start by a review of linear combination. You remember this topic from almost very beginning of this semester. So linear combination, for example, if you have two vectors, let's call one of them u and the other one v. If you multiply them by numbers and add or subtract, what you are creating is a linear combination of these two. So for example, 2u plus 3v, this is an example of a linear combination. So it has the two basic operations, the addition and scalar multiplication in it. Now the next level question is, if I have some vectors, say u and v and maybe some others, and the question is, out of these, can I build a certain other vector? Let's call it t. So u is given, v is given, and t is given. We want to know if t can be built from u and v. For example, suppose u is say 2, 3, and 1. V is say 1, 4, and say 5. And t is say 4, 1, and 3. Is there a possibility that I combine these two to arrive at this target vector? So this amounts to the following. What should I multiply this thing with? Let's call it A. And what should I multiply this one with? Let's call that one B. So that when I add them up, I get this. So today's topic is generalization of this idea and looking at the topic from a variety of different angles. The tool of the trade for answering the questions of this sort is going to be again that Gaussian elimination and that software we talked about. But before we dive into all the details of this, let's get a little bit of a motivation as to what this topic looks like and what are the things that we are going to do with it. So again, we talked about the linear combination, and our big plan here is that if I have a target vector, can I make it out of several other given vectors? Can something be built from several other things? Now, before we go down into the detail of this section, let me take you through a tour of some perhaps a bit game-like questions of similar nature, so that we see these general topics that we have here actually shows up in many other places. So what are the issues that we see here? We have some building blocks. Sometimes we allow to have ourselves to have many copies of them, and out of adding them we want to create something. Sometimes we want to know what are all the things we can create. So that is what the idea of a span is. Span is set of all the target vectors you can make out of certain set of vectors. Then idea of independence comes in. If you have some building blocks, sometimes you might think some of them are redundant. They can be kicked out, removed from the game, and you can just do everything you could do with the other ones. So that's the idea, general idea of independence. So we are going to talk about these things in detail. But before we go there, let me just take you through some array of websites I prepared for you. So Most of you are engineers, and probably you're going to work in some factories where there are these robotic arms that they do something. And I want to say there is some rather similarities between the issues you face there and simple issues we face today in our math class. So a robotic arm is made out of several components, which are each of them have very simple type of movement. But when you combine them, then the general movement becomes quite complicated. And what you want to know is that, well, what is it that you can do with that robotic arm? What's the range of it? What can it fetch? Where can it go? And so on. So the issue is, out of addition of several straight out movements, what are the final movements you can have? Okay, this is a very engineering type of topic. Yeah, I'm sure you know more about it than I do. Let me go toward more mathematical type of ideas. Uh, Next idea is in relation to the game of chess. Game of chess, one of the pieces that's quite interesting is the knight or the horse that moves in that L-shaped pattern. So there are lots of mathematical or recreational or computer science question that comes out of this this situation, where you want to have the knight go through all the squares of the chessboard without repeating its location and requiring that it covers all the squares. The question is, well, is such a thing possible? And if so, how can we arrange it? So you, for example, you see in this one, this is a 5 by 5 board, and the knight goes through all these stops. And this is the standard chessboard where some trajectory of the knight is shown here. So here the question is, we have a certain movement, that L-shaped movement of the knight, and the question is, if we keep repeating this movement, can we cover all the cells? So this has some similarity, is maybe thin similarity to the problem that we are going to look at today. Here's another example of a web page that actually can help you see what the process is going to look like. So if I have this knight started at this location 1, uh, this page solves for you what are the trajectory that the knight has to take so that it covers all the cells without repeating itself, and then there are further questions you can take a look at. So the similarity between this topic and what we are looking at is that by repetition of the certain movements, what are the feasible space that we can arrive at? Okay, another game that perhaps you are more familiar with is this game of Tangram. Maybe you got it as a gift from somebody and such. It's a very simple game. Well, simple looking game. It's made out of these 7 pieces, and the question here is, by rearranging these pieces, you're asked to make a variety of uh, designs. So they give you this design, and then they ask you to rearrange the pieces so that when you put them together, you get one of these. So that has a slight similarity to the mathematical problem that we have. If I have a target vector, can you build it out of certain other given vectors? Our problem, of course, is substantially simpler and more straightforward than this one, but there is just some slight similarity. Here's another page I have for you in the game of billiard. Suppose you have a pool table and there's no friction on it, and you kick the ball and it goes on endlessly. And the question is, if it keeps going on and on, what are all the points it can visit? So in which direction should I shoot the ball? And if you let it go, typically we don't have any pockets to worry about in this mathematical version of this thing. This thing goes on, and then you want to know what is the description of the trajectory of this ball as it goes on. Many versions of this problem. Uh, if the pool table is in the shape of an ellipse, you will see some very interesting pattern emerging out of this problem. If you look at the pool tables in the shape of these regular polygons, other problems come up which are quite interesting. And some people even extend it to 3 dimension. So if you have, imagine there was no gravity and this ball was being kicked and it's being bouncing around some shape in space. So there's no gravity, nothing preventing it, and it's just bouncing around. You can think about a ray of light, perhaps, those of you in computer science doing ray tracing. If such a configuration is considered, then the question would be what kind of a patterns can you get? Can you have a closed orbit and such? And here is a name that I was surprised to see here is Lewis Carroll, who is the author of that famous Alice in Wonderland. He has also worked on this problem, so that's a big surprise that this person has a track record in mathematics. He was actually a mathematician and he was a author. That was his hobby, but everybody knows him for his hobby rather than his contribution to mathematics. Actually, later on, we are going to come across some of his contribution. You might want to look up your textbook. The section on determinant has some contributions from him. So that is nice to know that mathematicians aren't just stuck to formulas. Okay, going back to the idea of a span. So the idea of a span is if we have several vectors, here I have 3 vectors, the blue one and green one and the red one, they're here in space. The question is, if I have a big supply of these things, imagine have like a Lego blocks. Instead of Lego blocks, we have just 3 types of vectors. They sit in space in a certain direction, all of them out of the origin. If we add them, which is like one of those game things, you are just making a construction, you're putting these things next to each other and making those parallelograms, and you add them. The question is, what are all the vectors you can build out of these 3? And in this case, it turns out all you can build is just this page that you see, this purple color page. As I turn it around, you see these vectors happens to be all sitting on that plane. From the other angle it was hard to see, but when we turn it around we see that by coincidence all of them are sitting on that plane. And however you add the 3 of them, you're stuck to this plane, you're always here. However, if I modify some of these entries, let's go to this page. So here I've changed some of them. Now these 3 are not on the same plane, and when I add them, I can make any vector in the entire space. Anything inside this 3-dimensional space can be built out of this V1 and V2 and V3. So if this was a sort of a mathematician's version of a robotic arm, a very simple looking arm, any place in this space can be arrived at by taking a multiple of V1 plus a multiple of V2 plus a multiple of V3, and then you can arrive at that location. This simplified game, we are going to call it spanning set. V1, V2, V3 is a spanning set for the entire 3-dimensional space, as opposed to this case. This case, there was something deficient about these vectors. They don't span the whole 3-dimensional space, because to begin with they are all on the same plane. which means they are dependent on each other, meaning one of them can be kicked out of the set, and we can still build the same set we can build with them right now. So it turns out one of these three can be removed, like a unnecessary component or redundant component. You can remove it and still build whatever you were building before. Okay, we made some very general remarks here just to say what our problem looks like from other perspective. Now we are going to go back to the mathematical side of this thing and start looking at these issues from a more precise style. So question number one. So we understood what the linear combination is. Very simple. We have just multiplication by numbers. It's called scalar multiplication. And then you add and subtract the result. Whatever we are creating is called the linear combination. And that linear combination is something like this: 2u plus 3v. You had the w also, maybe 5w, and so on. Now the difficulty, or one of those culture shock points that we were talking about in previous lecture, is what if we insist on looking at all the possible linear combinations? That word all, that's what's going to make problem a little bit difficult. What is a set of all possible linear combinations of a given collection of vectors? That's what we are aiming to understand in this lecture. Let's go after a simple question. So our first simple question is, suppose we are given some bunch of vectors. These are my u's and v's and so on. And then I have a target vector. The question is, can I build this target vector out of those? Think about it as a game of Lego. It's like some design. You want to know if you can build it out of those. Or just to remind you of this other game we were talking about, this one's of course substantially more complicated, a bit of a different flavor, is how would you build this design out of those pieces? Of course, in this case, you have a limited number of these things. You're not duplicating them all that much, except for these two triangles, which are same size. These are all different kind of pieces, and you don't have unlimited supply. But the question is, build this out of those 7 pieces, if it's possible. Here we have something of that nature, kind of, and the thing is, can you build this vector out of those? Well, if we write it carefully, you see that we have actually answered this question already. There isn't really anything new other than a terminology and a way of looking at things. So when I say multiply this by a and b until you get that, I'll go ahead and actually multiply. So you get 2a, and 1b, so 1b. That's supposed to be the first component, which is 4. And then next one is 3a, and then 4b, and that is supposed to be the second component. And then I have what? 1a plus 5b, perhaps, and that is supposed to be 3. Well, I have a linear system, the solution of which, if there is any, is going to be just that a and b that we were looking for. So to build a vector out of a set of other vectors turns out to be just solving a linear equation. This linear equation, we said at the beginning of the semester, can have one of 3 types of fates. It could be that there is no solution, which means this is not possible to be built out of those 2. It could be that, well, it is possible and there is just one way of doing it. Or it's possible and there are infinitely many ways of doing it. So you might see all 3 kind of scenarios in various type of problems, and then you set out and actually solve your problem. Now, if you want to write this thing in a matrix format, you say, well, my vectors, basis vectors that are given to me here, like 2, 3, 1, and the other one is 1, 4, 5, and then target vector is what we previously used to call the right hand side. So 4, 1, 3. So the name of this thing previously was right hand side, and now we kind of think about it as a target, like some points we want to arrive at, something we want to build. And this 1, 2, 3 and so on, these are the original vectors that they had given to us, which we are writing as we are writing these things as columns, and then we make our target, that's our right hand side. Okay, what is next? What's next is that if this problem is small, we do it by hand, and if the problem is big, we do it by the little software that we have. Either way, that would be fine. And let's go ahead and actually say do this thing by hand. How do we do this? Well, when we are doing by hand, we will always try to make life easy on ourselves, and the easiest thing to do is to use 1 as our pivot. Now, of course, 2 and 3 are not disastrously large numbers and such, but just to avoid mistakes with fractions and such, it's always best to go with smallest numbers for our pivots. One would be the best. So to do that, I just switch. So I'll have 1, 5, 3 on the top, and then I can have this 3, 4, 1 stays in place, and 2, 1, 4 came down here. Then what? So from here to here we exchange 1 and 3. Then what? Then I R2 minus 3 R1, and then R3 minus 2 R1. We are aiming to remove these elements. So I have 1, 5, 3, and then subtracting 3 times that. So first one we better get 0. 15 subtracted from 4, I get 11, and then this one I get minus 8. This one I get 0. Subtracting twice that from here, I get 9, and then subtracting twice that from here, so I'll get minus 2. Okay, now we said our numbers are gradually becoming unfriendly, but that's fine. I'll go ahead, make this thing into a 1, so I'll have 1, 5, 3, 0, 1 becomes 8 over 11. So I have row 2, I divide it by our leading number to make it be 1. That's a little bit easier to work with. Then we have 0, minus 9, and minus 2. Then I come here and say, okay, let's aim for this and use 1 as our pivot and this as our target, and we want to do 9 times row 2 added to row 3. So that's going to eliminate this number. And what do I get? I get 1, 5, 3, 0, 1, 8, 11. And this is becomes 0 and 0, and our last number is going to be minus 2 plus 9 times 8, 11. So let's do that. Minus 2 plus, this is 72 over 11, so it becomes minus 22 plus 72 over 11, and that is 50 over 11. Okay, what do we understand from this? Remember, these equations we're reading, this number times something plus that number times something is equal to the right hand side. So here we are really looking at 0 times a plus 0 times b is equal to 50 over 11. Well, that's obviously impossible. We said previously, if you have your coefficient uh, matrix with the row of entire zeros and right hand side is something that's not zero, then equation has no solution and we call it inconsistent. So no solution, inconsistent. And the way we express this thing here is, so let's write the question. What was the question? Is 413 a linear combination of 231 and 145? What's the answer now? No, there isn't, because I cannot find any a and b that solves the equation. There is no a and b that when you multiply it by 0 you get 50 over 11. That's just impossible. So the answer is simply no. But this is not a target of u and v. Well, what does that mean again? Let's go to one of these pictures that we had, see if we can, the picture we had, this one. See, these vectors, whatever you build from them, they sit inside of this plane. Now, if I am outside of this plane, if I'm looking at the vector outside here, I cannot build it out of these. There's no number I can find that I multiply by v1 plus some number times v2 plus some number times v3 that would be equal to some vector that is sitting outside here. So that is what is happening here. That's the meaning of this problem. It's always important to understand, well, what do these things actually mean? What is it that we are talking about? This vector is sitting somewhere in space, so let's write it like this. I'm just drawing something, not an accurate drawing, just some close by drawing. So I have the vector u, for example. Say this is u, and let's draw this one some v. Again, this is not accurate representation of them. So u and v, if I want to build something out of them, it's going to be inside the plane that contains u and v as direction vectors. If t is outside of that, so if my t is somewhere out here, not inside the plane of those, then I cannot build it out of those. And that's what we are getting at here. Can this t be built from those cases? And the answer is no. Okay. Now, when the problem numbers become larger, you have more cases to look at. Maybe you use that software, but right now let's go look at another problem that is small enough we can do it by hand. So let me give another example. Is a vector 1, 2, 3, let's call it t again, target vector, a linear combination of 1, 0, 3 and let's call this one minus 1, 1, minus 3. So let's call this one u and that one v. Is this t a linear combination of those two? So again, I investigated following. A times u plus b times v, would that be equal to t? Is there any set of A and B's that this linear combination is going to recreate that T for me? That's what we are after. Well, so well, actually go ahead and do it. So A times 103 plus B times minus 1 minus 3 is supposed to be my target. Any of these type of question, one of three types of answers. No, it's not possible. Yes, it is possible, and there's only one way of doing it. Yes, it is possible, and there are infinitely many ways of doing it. So always one of three possible answers can be given. Well, how does this go? Uh, convert all of your vectors to column vectors in a matrix 1 0 3 minus 1 1 minus 3, and the right hand side is your target 1 2 3. Well, you perform Gaussian operation or Gauss-Jordan operation, and you solve this, and at the end you get to the solution. Either you get a row of zeros here and the right hand side is not zero, in which case you're relieved to know there is no solution and you're off the hook. There's nothing else to do at this point. Or there is actually a solution, in which case you get an A and B. Now one of two things happens. Either you have only one possibility, or you have a bunch of parameters, in which case you have infinitely many possibilities. So all of that has to be detailed in the solutions that you give. So what do we do here? Well, luckily this is already a 1. I have to eliminate this thing. So minus 3 R1 has to be added to R3. You already see where we are going with this thing. Is that right? The first and the third row look mightily like each other, and that is what makes this thing work. When I add minus 3 times this to that one, everything on the left and on the right, they all get wiped out. Okay, when the right hand side also wiped out, we are a much better chance. Now you have a choice of doing back substitution or continue with the Jordan elimination. So when we are using the software, we prefer the Jordan style because it goes all the way to the very end, and we are not doing piecemeal work. So what do I do now? I take this, add it to that, so R2 added to R1, it makes 1 0 0. This becomes 0 also, and when I add it becomes 3 and 2 and 0. Now take this thing, rewrite it in that style, or let me write that as an equation so that you see this first equation really is 1a minus 1b is equal to 1, and 0a plus 1b is equal to 2, and 3a minus 3b is equal to 3. Well, if you write this thing as an equation, what is it going to read like? 1a plus 0b is equal to 3, 0a plus 1b is equal to 2, and 0a plus 0b is equal to 0. Well, last line is just an identity. 0 is equal to 0. That doesn't tell you anything. So this you just don't write at all. 0a is just 0. You don't write that. Of course you don't write. 1a is just a. So it's telling you a is 3, b is equal to 2. So nice thing about the Jordan style is that by the time you come to the this reduced row echelon form, you have everything you want to know about the solution anyway. So in this case, a is 3 and b is 2 means what? Means that if I take 3 times of this vector and twice that vector, I'll get my target vector. Let's verify. So we always ask to verify in these problems. Verify, first of all, you verify your answer. Second, you display, you understood what was it that you did. So what the meaning of this problem is that 3, or the solution of the problem is that if I take u and triple it, take v and double it, when I add them together, 3 and minus 2 is 1, 2, 9 and minus 6 is 3. Look, out of u and v we created our t. Again, sort of, let me just remind you one more time, we are playing a very simplistic game of, can you build something out of two other things? So this is a much more interesting version of that game. Here are 7 pieces, and you have to figure out which angle to put them and so on to make something come about. And our problem is a simple-minded version of this thing that you are making. You're playing with vectors, so things are a lot more plain, kind of featureless, not as interesting as those other games. But when you play this game, at the end you'll be able to play certain games at a much higher level. Okay, so out of this long list of things that we have in front of us, we have done the linear combination. We reviewed that. Given a vector t and a bunch of other vectors, how can we tell that t is a linear combination of all of those? Very simple. You make all of these vectors that are given to you, you make them as column vectors in a matrix. So a column vector, I draw them like this to indicate that we are listing them as column as opposed to rows. And then the target vector that you want, that's going to be your right hand side vector. That's another column. So this is going to be an augmented matrix with your coefficients here and right hand side here. You solve this thing with the Gauss-Jordan style, and your solution is in front of you at that stage. Okay, going on to next issue, span of a set of vectors. So span of a set of vectors, you're going to just make a definition now. So S there, S is a set. S is a set. So U, V, W, so on, whatever you have is a set of vectors. The idea of a span of a set, written like this, that means itself is a set of all linear combinations are vectors in the set S. Okay, now that was one linear combination, but when you have these vectors, you want to look at all possible linear combinations, and that's where the difficulty lies, wrapping our head around that. Why is that a problem? That's one of those culture shock things. This is, well, when you say all, means infinitely many different possibilities here, infinitely many other possibilities here. Consider all of them and tell me what is it that we are going to make from putting all of that result in one bag. Okay, we are trying to describe something that's like a big infinity but has a certain structure and look to itself. You want to describe all of that. Let's look at some simple cases. Suppose my set S is just one skinny set. It just has some vector u in it. Okay, so we are not making it so crowded. It's just one guy here, and I want to know what is the span of my set S. So let's suppose I have one vector. I have one lonely vector, nobody else to keep company with this vector. Well, what is a linear combination of one vector? Well, I don't have somebody else. How do I make linear combination? Well, all that you're left to do is to multiply it by some number. So for example, this vector you have, well, you can double it, huh? You can triple it, you can quadruple it, or you can multiply it by negative 1, you can multiply it by negative 2. You don't have to stick to whole numbers either. You can multiply by any fractional number, radical, anything. Well, if you look at all these output, one of them is of course 0 times this vector, in which case will be just tiny 0. How would you describe all of them? Well, very simple. The result is a line that lines up with u. Span of set A. So let's write it span of. Let's write it better here. So span of one single vector u, a line in direction, or the line actually, not a line, it's just one of them. The line in direction of u. Which u is assumed to be at the origin, and right now all of our vectors are at the origin, so it's not somewhere out in space. This is the origin of this space that we have. Span of u is going to be the line in the direction of u. One little fine print here we should consider. If your vector u was a tiny vector, it was actually a dot itself, it was 0. Now if you do linear combination, whatever you multiply with is not going to stretch all of those colorful things that we were drawing. No matter what you multiply this thing with, I'll get just a bunch of zeros all crowding at that center. It doesn't get to move. So here we have to write our fine print. If u is not 0, it's not the 0 vector, it has to have some extension, then the span of it is going to be a line. So let's to make it so span, if I have vector 0 there and I want to look at the output of this thing, this is going to be just a set consisting of the origin only. So if I have essentially nothing to begin with, there's nothing there, I cannot build anything out of them. If they give you a empty bucket of Lego pieces and ask you, well, what can you build out of them? Well, the bucket could be big, but if there's nothing in it, there's nothing for me to build. So if it's to begin with you have a 0 vector, well, all you can build is just that 0 vector. So that's kind of a trivial extreme situation. Okay, so span of one vector is just a line. Now let's go one level higher up. Span of, now suppose I have 2 vectors. What's the span of 2 vectors? So now we have looked at this problem several times. Let me draw different colors. So suppose I have a u and I have a v. I have a u and a v. And for a moment, in order not to fall in that trap, suppose we have this kind of a shape. I'll explain that later on. So I have a u and a v. Out of the linear combination of these two, again, the catch here is this word. Difficulty is here. Try to imagine all linear combinations of these vectors. For example, u plus v, 2u plus v, 3v plus u, minus u plus v, and all of them. All the linear combinations. So perhaps for yourself to visualize the situation, take 2 pencils, hold it in front of you, uh, just like this say red pencil and a blue pencil, kind of like this in front of you, and imagine, ask yourself, if I add these two, these are two vectors, if I add them in all possible ways and mark in space all the final vectors I get, what kind of a shape would be in front of me? Hmm? So I'm gonna ask you to think about this problem, and then we are gonna kind of come back and continue next time. So I want you to think about this thing. What is the shape that comes out of considering span of two vectors? Okay, so let's wait for the next lecture, and by that time hopefully you have the answer to this. So I'm giving a big pause here because this is a critical place in this section of the course. This section becomes a tad bit theoretical, so I expect you to come along and try to do some of this thing yourself. So critical question: what is span of two vectors? What's the set of all linear combinations of these two vectors? Okay, until next time, good luck and God bless.